Our first stop on this road trip of Colorado, Wyoming, and Utah is the Dinosaur Ridge. This is an amazing trackway with trace fossils and an amazing expedition center, and it shows the life of these dinosaurs through action more than body fossils. So I'm really excited to dive deeper into Dinosaur Ridge. This is the Dinosaur Ridge official front sign, and back there we have the Expedition Center. I'm so excited to get started today, so let's dive on into it.
The first stop on our journey to Dinosaur Ridge is the Expedition Center at their main site.
So the first thing you see whenever you walk into the exhibition hall is this really beautiful map of what the North American area would have looked like during the late Jurassic period, about 150 million years ago. So you have Africa and South America and the British Isles and Scandinavia and Europe over here. They're all drifting away, but you have the beautiful Sundance Sea right here. That was the interior seaway that actually disappeared before the Western Interior Seaway. But during this time, you actually had crocodilians that were there, just like in the modern time. This one is Diplosaurus, but was in 1890, was renamed in Germany, but that name doesn't matter. Back in 2010, they renamed it back to Diplosaurus. So this is actually a beautiful cast of a Diplosaurus skull. But here, we actually have the Camarasaurus, one of the most abundant sauropods in the Morrison Formation. Along here, this beautiful Diplodocids, Stegosaurus here, beautiful. You have this Allosaurus back here. This is a very beautiful example of some kind of estuary swamp-like environment, or dry swamp, during the Jurassic period. Now, one thing you'll notice is that there is no grass or flowers. Those didn't exist yet. So you had ferns and trees. And as we move over this way, you actually see how North America changed into the early Cretaceous, where the Sundance Sea had disappeared because it was coming from here. But then it actually started to drift back down, and a new seaway opened up, which was the Western Interior Seaway, which will open up all the way down and be just from the Arctic all the way down to Cuba and the Caribbeans will be open. But one of the big things about Dinosaur Ridge, if you know anything about Dinosaur Ridge, is they have the huge ridge with all of the footprints. That is the calling card of Dinosaur Ridge. This is an ornithopod. An ornithopod from this time period. These are actually reconstructions. These are not real, but they don't actually have any specimen from this specific dinosaur. But they don't actually have any specimen from this hadrosaur, but they have all the footprints of these hadrosaurs and these duckbills and these ornithopods, so they think that these existed here. Well, they know that they existed because of the footprints, but they don't have any bones. But if we turn around here, we get the sauropod exhibit. These are the giants of the Jurassic. We have the Brachiosaurus, the Camarasaurus, and the Diplodocus, or Diplodocus. Over here we have another Camarasaurus. This is a lower arm bone, the ulna, it looks like. This appears to be the ulna. But this is actually a beautiful representation. Camarasaurus and Diplodocus are actually the two most abundant sauropods in the Morrison, with Brachiosaurus being a lot more rare. Why? I really couldn't tell you. It could have something to do with the ecosystem, preservation, there's so many different factors. But this other beautiful Camarasaurus femur, just this big block of sauropod bone right here. But as we turn around, we actually see something really beautiful. These are trace fossils from aquatic creatures. So you'll notice you have bumps and burrows where you can actually see how they burrow in, which is, if you remember back to my episode I did about fossils, a trace fossil is not a physical body fossil, but it shows action. So footprints, burrows, feeding trails, pathways, anything like that that shows action within these creatures is a trace fossil. So you have these beautiful ornithopods, on the beach. So we actually have all these footprints, and this is just a mass trace fossil. And whenever we get to the actual wall, I'll go more into detail about that. But here we have some more recreations and casts of creatures that come from the area. So you have from the Cretaceous, you have Triceratops, Utah raptors, early Cretaceous if I'm not mistaken, off the top of my head, T-Rex, obviously Cretaceous, but we also have some of the Jurassic creatures, like the Stegosaurus or the Stagomyser is what it is referred to as the giant tail spike. You have these giant Allosaurus hand claws right here. One thing that's interesting about Allosaurus hand claws is they're meant for like digging in and holding on, so it actually has confused researchers what they're used for. Now here we also go to the early Cretaceous, where you'll see the slowly creation of this Western Interior Seaway. It's not all the way connected yet, so you don't have a full straight shot, but it is still an interior seaway. And down here we have some angiosperms and things like that, where these things first arrive. So you get like leaves, like better leaves and more things like that appear. You get flowers, those start to appear. You get a lot of the different kinds of leaves of angiosperms, they start to appear during the early Cretaceous, and they keep evolving into the late Cretaceous. If we come over here, again, we have just kind of continuing off of that background there, we have this continuing mat here, but here we have another trace fossil of a footprint of what seems to be an ornithopod. You can tell just by the shape, the ovaline back and the bumpier curved toes. If you come over here, we get some of the beautiful invertebrates with a vertebrate. You have ammonites and echinoderms. So these are shells, clams. The ammonites, obviously, you know them, you've seen them. You have ammonites, nautiloids, those are in the same family. And over here you have fish skeletons. Move that out of the way. If you get close here real quick. You have these indents of these fish skeletons in here, and you have this elasmosaur, where you can tell its teeth are very cylinder and pointed out, so that if a fish swims in here, it could close them and trap the fish inside to eat it. And building off of that, we have more ammonites. Ooh, they actually have this is something that I wish more museums would talk about, is the suture patterns, or the septal patterns. You can tell based on the evolutionary stage in time of the ammonite, based on the complexity of the pattern. So if you get close to this one, you'll see it's very, very, very basic, and then they slowly get more complicated till they're this very beautiful, complex, just star pattern. Then, of course, we go from ammonites to nautiloids. They're in the same family, they're connected. You actually have one of these, I'm pretty sure it is the most basic one, is the nautiloid pattern. So you can actually see a lot of these, of how they were. If you see those little bumps in between each section, those are actually to help with buoyancy. A tube would have ran through there to pump air through to help make it buoyant. Nautilus is actually still alive today. It is a living fossil, which is phenomenal. If we come over here, we have the king of the dinosaurs, the Tyrannosaurus Rex. This, just like if you remember back to the South Carolina State Museum, very, very beautiful example of geologic disfiguration or disconformities and things like that, where the bones are not just going to sit still, the rocks around them will crush and warp them and make them look like this. But this, again, just building off this. Tyrannosaurus, these huge, robust jaws, huge, robust teeth, massive head, tiny arms because the head was so massive, but this massive head meant for crushing and biting and just breaking and shattering. And you have another beautiful trace fossil of Tyrannosaurus footprint. And here we have the lion of the Jurassic, the creature that makes up 70% of the theropod fossils in the Morrison Formation, the Allosaurus. Now, this is my personal favorite dinosaur. These jaws are not as robust as the Tyrannosaurus. That is because they use the hack, like an axe kind of method. They'd take their jaws and shear kind of with them, and that's how they would attack. Now, you can tell the difference between, look at this massive Tyrannosaurus rooted tooth versus this. I think this is also another Tyrannosaurus tooth. That's unrooted versus what would be rooted. These are massive roots. And this is just absolutely phenomenal. And I mean, this Allosaurus is just a beautiful recreation. But if we come over here, we have more climate clues about plants, angiosperms, seed pods, ferns, coal. Coal is actually a huge giveaway to what kind of environment it was in, because it really only forms in swampy, murky environments. But if you come here, you have this massive vertebra, this absolutely massive vertebra, again, from another Jurassic giant. If I'm not mistaken, this one might be a diplodocid, I think. But this is what one of these massive, huge beasts, this is what their vertebra. This thing, I'm about 6 foot. Look at this thing compared to me. These things are massive. And this is its spine. This is its backbone. These are small bones. But if you come over here, we have another leg bone right here. These things are massive. It's literally the size of my wingspan. These are just massive Goliath beasts. This would have been its shoulder. This indent could be from anything, possibly a carnivore. But this is a scaled down Camarasaurus cervical vertebra, so the neck. Just another. So this is actually showing the two different. So this is Diplodocus. This is the two different Macronaria, and then the Diplodocoids. The Diplodocoids being the ones, their necks tend to be like that. Their faces a little elongated with the front teeth. Camarosauruses are necks up high, like Brachiosaurus is a good example of that, of Macronaria. And then if we turn this way, this appears to be another trace fossil, if I'm not mistaken. I can't really tell what this is off the top of my head, but if I had to guess, it's another footprint trace fossil. But we get into the final part, the late Cretaceous, which, this is actually a very interesting thing that they didn't show, was the full connection of the Western Interior Seaway. At this point, the Western Interior Seaway is drying up, it's disconnected, you can't sail all the way through anymore. But Colorado, the Dinosaur Ridge is still very swampy, still murky, so you have beautiful preservation of these giants and these behemoths like T-Rex and Triceratops. You have this massive Triceratops brow horn, and this is a very beautiful old school reconstruction of Triceratops. But thanks to this swampy environment, they were actually preserved very well, and we can actually tell a lot about their ecosystem. One thing I accidentally skipped over, though, before we wrap this part up, is they have this pteranodon here. These giant pterosaurs are very rare to find because their bones are so fragile, so hollow. They're just really rare to find. So when we find them, it's just an amazing discovery. But that is the exhibit hall, so let's move on to the next part of Dinosaur Ridge. The first sign we come across is the Benton Shale. Here we have our second stop, which is Colorado below sea, which would take us to the Western Interior Seaway 92 million years ago, whenever the West Coast and East Coast, Midwest to East Coast, were split by the ocean that cut through the center of North America. But here, these fine platy sediments, and fine-grained, are mud layers, one after another, that stack up. And in them, you find paddle-finned lizards, you find ammonites, you find nautiloids, you find fish scales. And those things tell us about the environment by telling us that they were a marine environment. So here we actually get a lot of things like clams, coiled-shelled ammonites, carnivores like sharks, so you could possibly find shark teeth in here, but also just the flat mud layers. I'm sure if you stack these up, you'd be able to see varves from the different seasons of the year. But also, since the Western Interior Seaway was salty, there's probably a lot of evaporite in here too, which is things like salts and pretty much salt. You get all kinds of different salts because, well, it evaporated, so the salt in the water had to go somewhere. Usually it sinks. A lot of the time it does sink and then it builds up. So you have mud and salt, and then all of the fossils in here will tell us that this was once below water. If we actually get right here, you'll see there's this beautiful textbook example of ripples. And what ripples are formed from is you have two different major kinds. You have the land and the water kind. So you have air blowing them, and they'll be very unsymmetrical, like sand dunes in the desert and things like that. But then you have the other kind from waves, where they wash sand onto shore, drag it back constantly, and eventually, if it hardens, you'll get this kind of formation where you have all these ripples. And this is just a beautiful example of ripples. This is just amazing right now. You have these giant gouges taken out. I don't actually know if those are from something or from like sample collecting, but it exposes a lot of these layers, these beautiful, beautiful layers, where you have the red, the blue, or not the blue, the red, the white, the yellow, those colors. It's a beautiful example. And the sandstone is very, very beautiful. And the red is actually probably from oxidized iron, where it would seep through. It'll seep through the sand and then build a layer, and it'll become oxidized. So that's why it gets that reddish hue a lot of the time. But this is just a beautiful example of just ripples all over this mound right here, which is also another example that this at some point was either a beach or near shore, or there was water nearby to cause these ripples. And here we have the Dakota sandstone, which is a sandstone formation. It's a very beautiful formation. So here is actually a beautiful example of these crocodilians that we were talking about earlier. If you look real close right there, I'll see if I can zoom in. It does not appear that I can. Maybe I can do this and get a lot closer. But if you look right about there, where the sign is pointing, obviously, you'll see crocodile scratches. That is most likely from them being ambush predators coming onto land to hunt Eolambia, which is the ornithopod I was struggling to identify earlier. I forgot what it was. Again, we didn't actually find any specimens of Eolambia, but we did find their footprints, so we do assume that they were here. But you'll see those scratches. Those could be from any number of things, from them pulling themselves out of the water, because again, this was near coast, near water, a swampy, murky area. Crocodiles would have lived here most definitely. It could have been from them lunging out of the water at an Eolambia. There's so many things it could be, but this is a beautiful example of trace fossils that show the nature and the environment more than like physical fossils could. And here we actually stand at the top of Crocodile Creek. Down there we saw the scratch fossils of the crocodiles pulling themselves out of the water, possibly at the bottom of the water, all kinds of things. But you can actually see, if you get close here, you can actually see these footprints of what was thought to be Eolambia all the way up to there. Now, rock layers are very interesting because the oldest is obviously at the bottom, the youngest is at the top, which is very interesting. So it tells a story. So you have this older layer with these crocodile scratches and this younger layer with Eolambia. This could mean so much. And the interesting thing about these track marks is that they're smaller than the main track site. So it could be a smaller relative to the species, it could be young Eolambia, or just a young animal in general. And they're coming up this mountain here. But at one point, this would have been flat, again, with water, with this creek cutting through. And the crocodiles probably were coming up and attacking these Eolambias, or these ornithopods. So this entire rock section right here could be telling an entire story about a crocodile hunting a young Eolambia. This is just a beautiful exhibition of like how the lack of physical body doesn't actually take away from the beauty of these trace fossils and how important trace fossils are. This is just a beautiful specimen right here. And this is like the first ones you see, and it's coming up here. It's like, all right, cool. You got the crocodile scratches. You're like, yeah. But then you finally see your first like footprints out in the wild. And I'm excited to see further. Here is a beautiful example of just behavior. These are from theropods. Now, according to this sign, they were 100 million years ago. But what this is display scratching during mating, and how birds today will dance and attract a mate. Dinosaurs did the same thing. They would move around, scratch their feet, and you can actually see a lot of these big old bulb chunks just gouged out. And I think that's what those were down a little ways when I said I didn't really know what those were. A lot of these bulb chunks taken out, like I mentioned down there when I didn't really know if it was from sample collection or something else. I think those are nest building sites, according to this. They are where the dinosaur probably would have taken a chunk out of the ground, laid some thatch or twigs or something down to lay its nest. And this is just a beautiful example of a giant, like, basically like mating, like a bunch of dinosaurs coming together to like mate and choose mates, with these scratches being display scratches where they would have scraped the ground. I'm sure if you looked hard enough, you could probably, under some of this that could have been covered up, who knows, there could have been examples of actual fights. These could have been possible fights too, between mates. It could have just been two dinosaurs mating. It's really hard to tell, and I doubt that one because of the number of nests that there are bulged around. But this is just a beautiful example showing behavior of these creatures that we don't really have a lot of behavioral example for. So these scratches are a window into the behavior. And if we come over here to this sign, it also talks about display scrapes, nest building, and reshaping of early nests. So you can see where the nest kind of would have been. There would have been one probably there, a couple up there, and these scratches just scraping away at the ground as some kind of display. I would love to see if somebody could figure out how to basically recreate this display into some kind of video so we could actually see what these dinosaurs did after identifying them. But again, these are ostrich-sized meat-eating dinosaurs, so probably not allosaurs, but according to this image, possibly something a little similar. But again, 100 million years ago, that's like right early Cretaceous, late Jurassic. No. Sorry, 100 million years ago, late Cretaceous, early Cretaceous. My bad. I was reading that wrong. So this would have been the Cretaceous, so not allosaurs. So here we actually have more of those ornithopod footprints along with a theropod footprint right there, but those ornithopod footprints right there. There looks like one right there and right there. These are beautiful, beautiful footprints showing up in this massive cliffside here, just showing us the life of these dinosaurs. And again, we come back over here for some more ripples, some textbook chef's kiss, beautiful ripples. And again, here's actually a sign talking about them. Moving water left behind from ripples in the sand of flat beach near 100 million years ago. So again, beach area, the water coming in and out, moving the sand and leaving these ripples behind, and eventually they harden and condense into sandstone, and you get these ripple marks, these beautiful textbook ripple marks. Starting from this end, going over, we have, it was said 39 species, 250 tracks representing both herbivores and carnivores, and a crocodile in here. So here we have some of those crazy ornithopod. If we come over, we'll actually see lots of these things trampling, going up and down and moving. And then here, we actually get our crocodile. This is where our crocodile is. You'll see those scrape marks on the ground. That's probably a nest of a crocodile, if I had to guess. Just these beautiful scrapes that just clawed away at the ground that are left behind now. But if we come over here, we get to actually see the difference here. This is the track site, is rated #1 in the nation by paleontologists. Here we have this theropod footprint. These are the estimates of the creatures. So we have this crocodile right here. We have this like ostrich-like ornithomimid is what they're saying it is. So if you get close to this track here, you'll see it's very slender, very thin. You'll have those unmistakable, just those unmistakable three points there. Those three sections coming together. Then it's very slender, so that's probably why they think it's an ornithomimid. But then you have those big, very wide, thick, robust feet that are similar. Those would have been the hadrosaurs, the ornithopod, the duck-billed dinosaur. These elephant-sized animals weighed around 3 tons and stretched about 25 feet long. And you'll see them all over here, all up and down this section, with the crocodile being over there. But then coming over here, you get the mud. You would get what would be the mud. So you have the ornithopod right there. These are the ornithopod tracks. These are very, very beautiful examples of them. So fluctuating sea levels and large coastal storms deposited alternating layers of organics like muds and things like that, sand, and again more mud over these once flat beaches, and then these ornithopods and ornithomimids and crocodiles come just tromping through it, and they leave their footprints behind. And then as that mud and sand in that shape hardens over millions of years, you're left behind with this footprint that shows you where these creatures were walking, how they were moving, how they were trampling along. And it's just like a beautiful sight to be able to actually like imagine how these things moved. And we actually get a lot of insight on how these creatures moved based on these footprints and things like that. So over here, this talks about the dinosaur behavior. To ichthyoologists, scientists who study trace fossils, things like movement through the trace fossils, track sites like this one offer a chance to study more than just the number of toes and foot shape of these ancient animals. Usually you'll find 2 or 3 trace of these footprints together, and you're like, this one's a triceratops, this one's a stegosaur. But this shows us so much. With those scrapes, we get so much from it. The skinny-toed carnivore have a great distance between tracks for their size, suggesting that they move faster clip than the larger, slower herbivores. So these smaller ornithomimids would have these long strides, so we're actually able to tell that they're running and sprinting and moving faster than these huge hadrosaurs and ornithopods. The herbivore tracks are mixed large and small in size, indicating social and possibly parental behavior. So if you actually look at some of these larger ones, you'll see some very smaller little dots kind of right near them. That would probably most likely be the young traveling with the mother or the father or the group or the herd all together moving. So you get this giant family unit. So you can actually see that these creatures stuck together whenever they were born. After they were born, they actually cared for the young. Hadrosaurs cared for their young through, and we know this through trace fossils like this, where the young are near the parental trackways, so we know that they were near there at the same time. And just this beautiful trackway gives us so much insight into ornithomimids and hadrosaurs alike. And down there with those scratches, it gives us into theropods and how they surprisingly acted like animals. It's such a weird thing to think about because we're so used to in media them being depicted as kind of monstrous, like Jurassic Park, Jurassic World, those kinds of things. But they're animals, and this shows that just animal behavior. They acted like animals. And I think this is just a beautiful look into what the life of these amazing creatures would have looked like. And here going into it, we see all these amazing bumps and burrows and little tiny holes dug out. We actually see another ornithopod track right there. But that's not what I want to point out. I want you to look at all these little gashes and things. That's actually more trace fossils from things like shrimp, worms, just creepy crawlies like that. And it shows these other smaller creatures that we don't actually think about in the fossil record that also make up the ecosystem. They would get in the mud and they'll trail around and they'd get around, and then the mud would harden and you'd be left with these trace fossils of those burrows and feeding tubes and feeding trails and movement tracks. So even these smaller creatures are preserved here at Dinosaur Ridge. So up here, we have a very unique structure, an iron concretion. Well, it's made of sand and iron. So you'll have the sand form around iron in the ground and it'll pull it up as the rock layer is lifted. So you'll get this weird bulb in the ground that's just iron. Now, we're gonna come over here and we're gonna talk about the volcanic ash, which is a very unique thing. You get a lot of things that form from volcanic ash. So if you actually look, you'll see a dark layer of just a strip of just dark layer, just right here. It's behind this little grate here. It'll be an ash layer. Now that happened from a volcanic eruption. So ash was spewed out and laid about everywhere. But as time went on, new sediments came and covered the ash. Now what that ash will indicate is an extinction event. So that ash will show you at some time hundreds of miles southwest, over 100 million years, a plume of wide-carried ash accumulated here at Dinosaur Ridge. 2, over time, be buried in compressed by heavy layers of sand and mud. So that is compressed ash. What was once several feet of ash became this hardened 2-inch layer called tungsten. It's tungsten right there. There are microscopic zircon crystals within the preserved ash, and inside those crystals is radioactive uranium. Uranium decays into lead over a predictable rate called a half-life. By measuring the amount of each element, scientists calculate that the numerical age of the layer at 104.6, giving or taking 37,000 years. So this, we're actually able to tell the age of this layer, giving us a beautiful indication of the layers above it and below it, being a very easy bookmark. So if this layer, if you follow it up and it's somewhere else and you find this layer, you're able to point to this one and be, okay, it's 104 million years ago. So everything in that layer below is 104 million years or older. Everything above it is older or younger. So it's just this easy, beautiful cue to just be like, boom, we know this time point, so we're able to figure out the next point and the point below it, and you're able to actually figure out different sections of the time period, and you'll see that there will be a lot of just debris, and it's an extinction event, so it's just a hard point in history to be able to point to and give a definitive time. So here you can actually see is a fault line, which is, this one is a strike slip is what it seems like. So the against each other and it's shifting everything. One side's going up, one side's going down. So that's why you get sides that are higher and it's slowly tilting. So that's why everything looks like this. Now coming over here, we have another set of tracks that are very rare. We have raptor tracks, a slightly large cousin of Asia's velociraptor left the track in the soft mud around 105 million years ago. So actually, surprisingly, during the Cretaceous, a lot of creatures came from Asia due to a land bridge coming from Alaska, connecting Asia, not necessarily Alaska, but Asia to North America. So that's where we get tyrannosaurs, raptors, and things like that from. And you can tell it's a raptor track because it looks like a theropod track, but one of the toes is missing, indicating that sickle claw that would have been up. So you actually, if you look right there, it's circled in for you. It's very beautiful. It might be hard to see on camera, but you can see the definitive two toes and then the one that kind of comes off that's missing. That would have been the kill claw or the sickle claw, indicating the raptor or the dromaeosaur lineage. So here we have this more layers, more rock slanted like this. And you'll notice this really weird, just bulging down section here. That is because it is a footprint. The dinosaurs stepped down and we're getting like a side view of it being compressed into the mud. So this would have been a mud layer. All of this would have been one mud layer. And the dinosaurs stepped and pushed that mud layer down and it hardened and turned into rock. So now you have this just preserved footprint that doesn't look like a footprint in this weird bulge, but it's actually a footprint. Now, if we follow this some more, you might notice a few more. They're calling these bulges, but right here, you have another one of what appears to be a that one was probably a hadrosaur or a ornithopod of some kind. This one seems to be a diplodocid or a diplocoid or diplodocoid, depending on whatever you want to talk. Again, you have this one long layer here, this one really massive layer here, and then it just has this giant bulge just step down. And that is where this diplodocus or diplodocoid stepped down into the mud again, and it's this massive section here. All of this is one giant footprint from where this giant sauropod stepped down. And following again some more, it appears we have another diplodocoid up here. Again, you have the one giant layer section right here. If you look where these, maybe I can get this with the light. Nah, probably not. You get this giant section, it looks like these little grain, scale-like pattern for lack of better words. You see this giant bulge down. Another sauropod stepped there and left its giant footprint and pushed the mud down. So you get this footprint left on the side from the mud, and now it's been exposed so you can actually see this footprint, and it's just left behind as this just beautiful remnants of showing that these diplodocoids where they lived. And there's another one right there, just this giant bulge that's just coming down, and this is actually part of a theory that some paleontologists have. Again, every one of these theories is probably debated amongst paleontology because half of it is guesswork, if we're being honest. Diplodocoids actually most likely lived in swampy waters and more swampy environments, and Camarasaurus lived on more plain, not fragile, but just plains with more trees, less swamp water. So these are actually probably diplodocoids because this was probably more of a swampy area of the Morrison Formation So we actually get these footprints from these diplodocoids. Here we have the Morrison Formation. Again, the Morrison Formation is more than just this. It encompasses all the way from Montana down to even parts of Texas, if I'm not mistaken. Chunks of Colorado, of course, Wyoming, Utah with Dinosaur National Monument, all part of the Morrison Formation. But this is a beautiful example of just a section of the Morrison Formation. It's just massive, massive section. And the Morrison was home to most of your sauropods of North America. They kind of disappeared and dwindled off into the Cretaceous as far as we're aware, but you get the start of the macronarias and the diplodocoids during the Morrison. You get stegosaurs, you get early ceratopsians too. A lot of people leave that one out. You get early ankylosaurs too. You get the allosaurs, the ceratosaurs, the allosaurs later turning into the carcharodontosaurs, the ceratosaurs later turning into the abelisaurids. And then in the very late Cretaceous, or not Cretaceous, the late Jurassic with the Morrison Formation, you even get early tyrannosaurs, which of course turn into Tyrannosaurus rex. Now, if we actually come over here, it's a bit of a walk down here. We have some theropod tracks somewhere right here. These beautiful theropod tracks, and you can tell they're a theropod by the big 3 toes and this nice angular just backside with these giant claws here. This was most likely a theropod, and since this is next to the Morrison Formation, my best guess, not just because this shows it, is this is an Allosaurus. My assumption of this is because Allosaurus was 70% of the Morrison Formation theropods, so the likelihood of this being a Allosaur is very high because they make up most of the theropod database there. If you think that this theropod track looks like a bird track, you're not far off. Modern birds share many similarities with theropods, including a foot structure. Modern birds come from the lineage of theropod. They come from non-avian dinosaurs into avian dinosaurs. No T-Rex did not turn into birds. No Allosaurus did not turn into birds. No Velociraptor didn't even turn into birds. It's just an entire lineage that just keeps going. It's very complicated. I have episodes up about the theropod family tree that I created that shows that. But this is just a beautiful, beautiful textbook example of a theropod track right here. Here's our last stop on the dinosaur trip. Fuck. Walk up towards you, or well, yeah. Here's our last stop on the Dinosaur Ridge pathway here. We have what I know everybody immediately thinks of when they say fossil. Dinosaur bone. So this is the actual bone of a diplodocid, according to this sign. These are diplodocid bones just embedded right here for people to look at. Look at this beautiful shiny material. This is probably replacement fossilization. So the groundwater with mineral-rich groundwater will pack this down and seep into it and replace the actual bone with minerals like quartz and silica. So this is actually technically a mineral, but it's not at the same time. It's very, very crazy, and I think it's very interesting. And this is a beautiful dinosaur bone right here. And as we walk down here, we have some more. I can't exactly tell you what these are just by looking at them down here, but we have this bone right here and this giant chunk of bone right here. This could be anything from an ulna and a femur to a femur, or even possibly part of a vertebra that's been deteriorated over time, and this is the only part exposed. It's very difficult to tell when it's still in the wall like this. And I think that is it for the wall right there. But if we come over here, we have these beautiful Morrison Formation bone bed signs where some of the most iconic dinosaurs like Brontosaurus and Diplodocus or Diplodocus come from other sites within the formation. Dinosaur Ridge is home to the world's first Stegosaurus. This is where Stegosaurus was found. There are more accurate and better specimens like Apex that come from different areas, But this is where Stegosaurus was discovered, and Apatosaurus specimens, this is where Apatosaurus was discovered. Same with Stegosaurus. And you can see their bones scattered here in the sandy layers. Other remains include Allosaurus and Camarasaurus, and newly discovered have revealed lungfish, crocodilians, and turtle fossils. So you have this chunk right here. So I'm sure you could spend hours and hours just coming over here and examining this wall. I'm sure there's so many chunks like this right here. This is probably fossil right here. Looking at it up there is probably some fossil as well. Up right here, more fossil. This could be from a stegosaur. This over here looks like some fossil as well, embedded in the sediment. This could be Allosaurus and Stegosaurus and Diplodocids and Apatosaurus. You get all of the beautiful Morrison formation, just famous creatures here at Dinosaur Ridge. It's a beautiful example, and I think these fossils are amazing to look at because it shows not only on the other side and even parts of this side with the trace fossils and the footprints of the action of the creatures, you get the actual physical remains of these beautiful, majestic creatures that lived so long ago. I think this is a beautiful sight because it also combines that just heavy, physical, objective fossil body part there with the trace fossil that lets you share the imagination of this creature could have been over there doing something and caused some of those tracks. It's really up to speculation sometimes. And I think this is a beautiful place to come visit if you want to come see some beautiful trace fossils along with some fossils naturally in the wild. I also wanted to take a second to show off this amazing plaque dedicating Dinosaur Ridge. Look at this, another fossil right here, right above this plaque. Just beautiful connection right there, showing that this plaque telling us that we have such national natural landmark has such just value with these beautiful specimens. And even if we turn right here, coming down these stairs that were man-made, you see more fossil right here. Here, all down this side, it looks like fossils here. And even over there, down here, all the way down here, you come down these naturally man-made stairs, and this boulder right here has more fossils on it, just right here, just for you to look at. It's amazing, it's beautiful, it's just right there. And it just shows us that the burying of the bones, you have this river come through here and wash all these creatures down and bury them quickly. And so you get this beautiful bone just right here out in the open, millions of years later for us to research and study. It's just a phenomenal place with a lot of just rich natural history to it. So this was Dinosaur Ridge with their amazing trace fossils, bone bed, and expedition center. I'm so excited to see what comes next for this road trip.